Hi everyone. Today we'll learn about the AWS F1's DRAM architecture and some related optimizations. Remember that we ran the Hello World project on FPGA at the beginning of this course. It turned out that the Hello World project was just a vector add kernel, but somehow it was programmed in a little bit complicated way. It has a separate function that reads in 1 and in 2. And if you go into these functions, it's just a for loop that does data copy. This code also has another function that does just the addition on the read data. And the result is written using yet another function. Considering the simplicity of the vector add operation, such coding styles seems a little bit like overkill, isn't it? So, what I'm going to do today is first explain the optimizations already applied on the Hello World project. And second, explain the ways to further improve the implementation considering the AWS F1 DRAM architecture. So today's learning objective is to be able to explain the DRAM architecture of AWS F1 and understand the reason for the low effective bandwidth in a vector add application. And we'll optimize the DRAM access architecture with the Vitis and the Vitis HLS. Let's first look at the inputs and outputs of AWS F1. AWS F1 is connected to the host CPU through the PCI interface, and F1 also has some ports that allows you to connect to other FPGAs. The rest of the pins are mostly used for the external DRAM interface. There are 4 DRAM channels, and all 4 channels can be accessed independently. Now, let's think about the connection between the kernel and the DRAM channels. Vitis expects the communication between the kernel and the external memory will be in AXI bus interface. That's why we define the HLS interface programma in m_AXI for the Hello World and the FIR projects. AXI runs at 250 megahertz, same as the kernel, and the bus data bitwidth is 512 bits. Now, let's try to calculate the ideal bandwidth of the DRAM channels. Since there are 4 DRAM channels, it'll be 4 times 0.25 gigahertz times 512 bits divided by 5 bits per byte. So the ideal DRAM bandwidth is going to be 64 gigabyte per second. Of course, we can't really reach the ideal bandwidth. This is a bus, so there's going to be some arbitration overhead and other control overhead as well. But we'll try to get close to this number as much as possible. The Hello World project already has a number of optimizations, so let's take a step back and assume that we have the following HLS code for vector add. This is a very intuitive coding style for vector add. You can see that it only has a single for loop, which takes an element from in 1 and in 2 and add them together and write the result to out. It also has a pipeline programma which should pipeline the addition operation. So assuming that we have made such code for the vector add task, let's try to calculate the effective DRAM bandwidth of this code. This is the experimental result if we run that code on AWS F1. I have set the vector add length to 256 million elements. The time taken to execute the task was 29.2 seconds, and we want to calculate the effective DRAM bandwidth. For the calculation, we need to make an assumption that is the vector add kernel is a memory-bound application and spends most of the time transferring data. Then the effective DRAM bandwidth is going to be size of the transfer data in bytes divided by the time taken. We are reading in 1, in 2, and writing out, so we fetch 3 data for each vector add length, and each data is in unsigned int. So the bandwidth is going to be 3 times 4 bytes times 256 million divided by 29.2 seconds. So if you do the calculation, it turns out that we only achieved effective bandwidth of 0.11 gigabyte per second. Since the ideal DRAM bandwidth is 64 gigabyte per second, the effective DRAM bandwidth is way too small. So let's see why we get such a low bandwidth. The first reason for the low bandwidth is the narrow bus data bitwidth. The physically available AXI bus data bitwidth between the kernel and the F1 DRAM controller is 512 bits. But if you make a kernel code with the top function argument type of an unsigned int, the synthesized bus data bitwidth is going to be 32-bit. This can be confirmed from the waveform. If you run either Vitis HLS cosim or the Vitis hardware emulation, you see that the bus data bitwidth is indeed 32 bits. So we're not fully taking advantage of the available memory resource. There are 2 ways to solve this problem. The first method is to use a wide data type. That is a user type APU int 512 for the top function argument. We have seen this type in the fixed point representation. It means that we're using a custom bitwidth type of 512 bits. So we're going to change the top function argument like this. Now, the problem with this code is that the data was originally in the unsigned int type, right? So if you start fetching data in an APU int 512 type, we need to divide the data into the original data type. To achieve this, you want the range operator where you specify the high and the low bit between the parentheses. So if you look at this code, you can see that you first fetch data from in1 and extract the first unsigned int by selecting the range from bits 31 to 0, right? The second element can be extracted from the bits 63 to 32, right? And so on. And you can also do the same for the int2 argument as well. The next step would be to do the addition in the original data type, like this. After doing the addition, you obviously want to concatenate the result back into APU int 512 type because you want to write the result back to DRAM in 512 bits as well. So you can do the concatenation by using the parenthesis and the comma operator. So for example, you can write the parenthesis, one of the element, comma, the next element, comma, and so on. And you can use another parenthesis to close the concatenation. And after doing this, if you run a cosim, you can confirm that the bus data bitwidth has indeed been increased to 512 bits. There is another way of widening the bus data bitwidth. You can use a vector type for the top function argument. So Vitis HLS has recently started supporting the vector type. You can use the HLS double colon vector. But if you're going to use the vector type, you have to decide on the length of the vector. If the base type was in unsigned int, you can set the vector length to be 512 bits divided by 32 bits, so the vector length of 16 elements. But if the base type was short, it'll be 512 bits divided by 16 bits, so a vector of 32 elements. Okay. The code would look like this. You can change the argument to use the vector type. For the addition, you don't have to divide up the vector to individual elements like the APU into 512 type. You can simply add two vectors. And the Vitis HLS automatically performs addition on 16 elements per iteration. So vector type is quite convenient. You can use either the Y data type with the APU int or the vector type. The result is really quite similar. It's just that the hello world example is taking the second approach. Now I will describe the second problem. Let's go back to our vector add code and interpret this code word for word. So we'll fetch one element from in1, fetch one element from in2, do the addition, and then write the result to out. Go to the next iteration, read the next element of in1 and in2, and add and write the second result to out. This behavior is shown in this timing diagram. Read in1 and in2, add, write, and then go to the second, read the second element of in1 and in2, add, and write out. But this timing behavior is too inefficient because we can read the next element of in1 and in2 while doing the computation of the previous element. We don't need to wait for it to finish. Same problem occurs with the data write as well. So what we want to do is overlap the memory access and the computation. So after reading an element from in1 and in2, we can let the adder do its job, and in the meanwhile immediately fetch the next element of in1 and in2 arrays. This is shown in this timing diagram. We're going to obtain high performance because the memory access and the computation is overlapped and done in parallel. So the way to overlap the execution of functions is called the Dataflow optimization. This is enabled by the Pragma HLS Dataflow. The Dataflow Pragma allows the functions to execute in parallel even if there is a dependency between them, so we can achieve a high performance with the Dataflow optimization. In Dataflow mode, some functions will produce data and some will consume data. If data does not arrive, the data consumer functions will simply wait until the producer function makes the data for them. So to make this happen, we need some kind of data buffers between the functions, and we use FIFO for this purpose. FIFOs are instantiated using the keyword HLS stream, and you can specify the type of the FIFO between these brackets. You can find a perfect example of Dataflow optimization in the Hello World project. So if you were to revisit this code, you can see that it has the Dataflow Pragma, and it will allow the 4 functions to execute in parallel. the load input 4 in 1, load input 4 in 2, compute add, and store result. The load input 4 in 1 will read the data one by one and pass the data to compute add using the FIFO interface. You can see that the FIFO was instantiated in HLS stream with the vector length of 16 as the base type. And you can give a name to the FIFO. Also, it is a good coding practice to initialize a stream in this way. Okay. So now you know why the Hello World project is coded in this a little bit complicated way. The purpose is to enable data flow optimization and achieve computation memory overlapping. But there is a reason why I kept putting old solution in the title. In the recent version of Vitis HLS, computation memory overlapping has been automated. It is actually one of the main difference between the old Vivado HLS and the current Vitis HLS. So explicit data flow optimization is no longer necessary, well, at least for the purpose of the computation memory overlapping. But I'm not saying that data flow optimization is completely meaningless now. In fact, it is still a good practice because Vitis HLS sometimes still misses function level parallelization opportunity. And we're going to see some examples of this in the next chapter. So let's look at the performance after applying solutions 1 and 2. The execution needed to do vector add for 256 million elements was 0.236 seconds. And if you compute the effective DRAM bandwidth, it'll be 13.6 gigabyte per second. This number is a huge improvement compared to the baseline version without this optimization. Which is great, but it is still a little short of the ideal DRAM bandwidth. This means that there is still some room for improvement. The third problem that is stopping us from reaching the ideal DRAM bandwidth is that we are not using all the DRAM channels. All top function arguments and the corresponding OpenCL buffers are assigned to a single DRAM channel by default. Since there are 4 DRAM channels on F1, we cannot utilize the full bandwidth unless data are distributed among multiple DRAM channels. So here's one example allocation for higher effective DRAM bandwidth. We can assign in 1 and the corresponding buffers to this channel, in 2 to this channel, and out to this channel. In this case, we can utilize 3 out of 4 DRAM channels and thus increase the effective bandwidth. So let's see how to implement this. That is, we want to map top function arguments in 1, in 2, and out to separate DRAM channels on AWS F1. To make this happen, you first need to edit the make file. Look for the line that uses VPP flags. And next to that line, add the flag connectivity.sp vad_1.in1:DDR0. So this is the argument name, and this is referring to the DRAM channel. And using the same flag, you can map into and out to DDR1 and DDR2 as well. The second thing you should do is edit the kernel file. To edit the kernel file, you need to learn a new concept, which is bundle. A bundle corresponds to an independent XE master, and the kernels use bundles to access DRAM channels. What we want to do is use a separate bundle for parallel access, so we can let in1 to use XE master to access DDR0. and allow in2 to use another bundle to access DDR1. Same for out and the DDR2. To assign different bundles to different arguments, you only need to assign a different bundle name. The original Hello World project uses a same bundle name for in1 and out, which is GMEM0. You can tell Vitis to use different bundle by simply changing the bundle name of out to something else like a GMEM2. Okay, now GMEM is not a keyword, and you can pretty much use any name you want as long as the bundle name for each argument is different. Vitis will recognize that you want to use a different XE master. Okay. Here's the performance after applying solution 3. The execution time for doing vector add on 256 million elements was reduced down to 0.082 seconds. Then the effective DRAM bandwidth is going to be 39.2 gigabyte per second. Since we're using only 3 out of 4 DRAM channels, the ideal bandwidth in this particular memory assignment is going to be 64 times 3 over 4, so 48 gigabyte per second. So we still haven't reached the ideal DRAM bandwidth, but like I said, we can never achieve the ideal bandwidth because of the various overheads. And it's pretty good that we have achieved 39 out of 48. It tells us that we have done the optimization correctly. So if we compare with the baseline implementation that just had a for loop and adding on the unsigned int type, it has a very low effective DRAM bandwidth, right? Using the vector optimized version or the Y data type leads to a much higher effective DRAM bandwidth. And I've told you that applying the data flow optimization here does not change the bandwidth too much for this particular kernel. And we can further improve the performance by using multiple axes and multiple DRAM channels and achieve 39.2 gigabyte per second, which is very close to the ideal DRAM bandwidth. But for solution 3, there are some things you need to consider. First, using additional bundle and DRAM channels require additional FPGA resources because you are instantiating additional controllers. So this technique, solution 3, will increase your FPGA resource utilization. Second, you need to consider other kernels running in parallel. It is possible that overall performance might be better when independent DRAM channels are assigned to other memory-bounded kernels. You know, DRAM bandwidth is a precious resource on FPGA, and you need to think about how to assign DRAM channels to the right kernels to maximize the overall performance. And of course, as a general advice, please try to pass data directly to other kernels whenever possible, and not consume DRAM channel. Okay. Here's one of the paper that discusses the effective DRAM bandwidth and the latency of the recent heterogeneous CPU FPGA platforms, including AWS F1. So you're welcome to refer to this paper if you're more interested. Here's a summary of today's lecture. So AWS F1 is composed of 4 independent DRAM channels, and you can use a wide uint data type or the vector type to utilize the 512 data bit width of the XE bus. We also learned that the function execution can be overlapped with the data flow optimization, and also the DRAM access modules may run independently when mapped to different bundles and the DRAM channels.
And that concludes the discussion on the AWS F1 DRAM architecture and the related optimization. In the next class, we'll go to a new chapter that uses some of these optimization we learned in this lecture. And I'll see you then.